Hello, okay, so this is chapter 5, Hydrograph. So the content, of course, first we will understand back what is hydrograph, so what are the basic components of hydrograph. And then this is also really important. We will learn how to develop unit hydrograph. So what is unit hydrograph? And also what are its application? So what are the basic components of hydrograph? Okay, so what is hydrograph? It's actually uh, a chart of discharge against time. So the basic component of a hydrograph you must understand is that it has some inclination, okay, and then it have peak and it will have some recession. So all of these have some meaning, okay, because hydrograph is actually we use it when there is a storm or rainfall. So when there is a rainfall, then we will have this kind of discharge pattern, inclination, rise of the limb, peak, and then some recession. So what do you mean by this? Inclination means that when there is rainfall accumulated of runoff, then it will go into the river. So the hydrograph or the discharge will show some rise, okay, and then there will be some peak, where after the peak there will be some recession. So recession occur when the rainfall are becoming less, so the runoff are also less, so then the flow in the river will recede. So if we have a hyetograph, okay, and we plot the same timeline if you want, or it doesn't matter, but what's important here is that once the rainfall peak, okay, so there will be some lag time, okay, once from the peak flow to the peak rainfall. And what else? And you remember that we learned about Horton curve. So this shows this is a recap from previous lecture. So this shows that, okay, above this Horton curve are the excess rainfall, or these are the runoff, the surface runoff. So these are the surface runoff, okay? And underneath the line, the loss curve, then that is the infiltration occurring. Okay, so this surface runoff is the same. If in terms of volume or in terms of depth, it is the same with the excess or effective rainfall. Okay, so if there is no storm, if there is no rain, then it's just base flow. If there is no storm and rain, so it's just base flow. Okay, and this is where the river is at a constant, quite constant level or discharge. So again, when there is rainfall, some infiltrated and some becomes overland flow or surface runoff, and they go inside the river. So these are the additional volume or discharge going in the river. So you will have the this bell shape of the hydrograph. Okay, so again, just to really make sure that you understand, okay, if we have a total rainfall, then there will be some effective rainfall and some are losses or infiltration. So again, surface runoff goes into the river. Okay, so these are the additional discharge during storm, and the base flow of from groundwater. Okay, and please remember, if there is the curve, Horton curve, or also phi index curve, or phi index line, so it separates what we know about what is surface runoff and what is base flow. Okay, so for also for phi index, if there is the phi index line, so we know that above the line is the Above the line is the runoff, okay, surface runoff, the rainfall that contributes to the surface runoff, and beneath the line is the infiltration. Okay, but for hydrograph, the question is, how do we separate the surface runoff and base flow? Because if we get the data, we will only see this kind of shape. Yeah, we will only see this kind of shape. So we need to try and separate what are the surface runoff and the base flow. Okay, because what we have from the total runoff is the the total rainfall is the surface runoff and infiltration, but when we observe the hydrograph, it's the combination of base flow and surface runoff. So we need to know what is the line that separates base flow and surface runoff. Okay, so there are several methods to separate this surface runoff and base flow line. Okay, one of the simplest method is you just consider it as the straight line. Just consider as the base flow as the straight line, a horizontal line before the climbing of the limb, or before the inclination, and right after the recession of the hydrograph. So just put a straight line, so we can say that is the base flow. Okay, another method is that if we know that catchment, and we know that after peak flow, and we know that the duration taken for it to become the base flow again, for example this point E, so we may just use that information. Okay, there are also ways to estimate this end day, but the best is to use historical data for estimating the end day. So this is just a guideline of how you estimate the line. For example, you know that this is a straight base flow line. Okay, means that no runoff goes into the river. So you know this is A. So you know the end day. Okay, so this end day, this end number, this duration, we can get it from historical observation. Okay, or there is some theory available on the end day. Okay, and so we just estimate that way. Okay, and the and number 3, okay, there is the method master depletion curve. So this is the most accurate and in terms of analysis, because it uses also historical continuous stream flow records, and it has some analysis in it, compared to the end day. It's just from observation, but this one also from observation and also some analysis. Okay, so it is based on the historical stream flow records. Okay, and conventionally before we use tracing paper, but now we have Excel. We may use it using other platform. Okay, let's say we have historical stream flow records, Q against time. So you see there is a lot of storm events, a lot of inclination and recession, inclination and recession. So these are all due to some storm events. So okay, so from this historical data, okay, let's say we know the peak A, and then B. Okay, B is the recession, the lowest point for this storm, for the storm that produces the peak A. And then we have C, D. So we identify this, and the peak and the lowest point, the peak and the lowest point, and the peak and the lowest point, for example. Okay, so when we have the data, we organize the data from the highest flow to the lowest flow. For example, event AB, this line, event CD, event EF, Okay, so these are organized from the highest values to the lowest value. So remember, A, B, C, D, E, F, these are all events from storm. Okay, so then we try to plot it, okay, and log Q. Okay, before we have Q, but now we log the Q because we want to have some kind of a straight line, a linear regression line. So we log Q. Okay, once we get that line, remember we got the line, the linear regression line. Then we may convert the line to Q, anti-log it, so that we can get Q. So we have this master depletion curve linear scale line in tracing paper. So this is conventional way, we draw it in a tracing paper, but we can also do this line using Excel. We can create this line using Excel. Okay, so once if we have a single storm or a single hydrograph, then we try to match this curve, okay, to the recession line of, this is the recession line of the Q, and try to match this the curve. So this is the important, this part. Try to match this and make it fit, then we can say that this is the F, the point. So next we can draw from point A to this F. So this is what we assume. Okay, so underneath this line is the base flow. Alright, so we learn how to separate from the original hydrograph. We separate the runoff to the base flow. Okay, so now we go into unit hydrograph. So what is this unit hydrograph? Okay, so the concept of unit hydrograph was introduced before by Sherman since 1932. It was a long time ago. Okay, the concept is actually simple. It's a simple concept, but you may need to have the imagination to understand it. Okay, so what is UH? What is unit hydrograph? Okay, by definition, it is the hydrograph. So remember, a hydrograph. So this is a hydrograph. So this is Q, meter cube per second, and then this is time, right? So the hydrograph that results from 1 unit of excess precipitation. So if you need to recall back, let's say this is the rainfall, okay, and then you know that there is some curve, the infiltration curve, and you know that this is the what do you call this, the excess or effective rainfall. So you want to convert this excess or effective rainfall. Okay, you want to know this. If you have this amount of excess rainfall, what is the hydrograph? Okay, if you have this amount of excess or effective rainfall, what is the hydrograph? And you want to develop a hydrograph based on information of your effective rainfall values. Okay, so for example, if you know that this excess rainfall is, the total of this excess rainfall is 100 millimeter, let's say. Okay, 100 millimeter. So you want, what if it is a 1 millimeter effective rainfall? So what is the hydrograph, or what is the hydrograph? So what is the runoff volume? Okay, I'm shading the runoff only. Okay, what is the runoff volume for a 1 millimeter effective rainfall? Okay, so this unit hydrograph is a production of a 1 unit of effective rainfall, or 1 unit of the excess precipitation. So remember, excess precipitation and effective rainfall is the same thing, and it is the it has the same volume of a runoff. So that is why if we have a 1 millimeter effective rainfall for a certain catchment, so what is the production of the unit hydrograph? Okay, so this shaded, I'm shading it again, this shaded area is the runoff. So it is for unit hydrograph. So let's say this is the unit hydrograph. So the runoff for this unit hydrograph is a production of a 1 millimeter effective or excess precipitation. Okay, so when you write down the unit hydrograph description, like here, T unit hydrograph, TUH. So T means the duration of the effective rainfall. So where is the duration of the effective rainfall? So you know this is the effective rainfall. So the duration is, let's say this is 3 hours. Okay. Okay, you see this figure. Okay, so the duration for this effective rainfall is 3 hours. So the production of this effective rainfall for a certain catchment for the unit hydrograph, so it is the 3-hour unit hydrograph. 3-hour unit hydrograph. So this is the concept of unit hydrograph. Is a product of a 1 unit excess precipitation to the hydrograph. So it is called unit hydrograph. So every catchment have different unit hydrograph. Okay, so why do we use this unit hydrograph? Is if we know other storm, we want to identify what is the hydrograph. It's just to estimate or develop a hydrograph from a known historical or observed storm before. So we produce unit hydrograph. So you may understand this later with example. Okay, so similar as I explained in the previous slide. So this is again a repetition of what is a unit hydrograph. So I hope this might be more clear. So in practice, a T-hour unit hydrograph is defined as a resulting from a unit depth of effective rainfall falling in T-hour over the catchment and is labeled as TUH. So remember I told you about the excess or effective rainfall. So if this effective rainfall is T-hour, right? Let's say it's 3 hours, so it is a 3-hour unit hydrograph. Okay. Okay, so what is this figure explaining? Okay, so this is just let's say the effective rainfall is 100 millimeter, for example. So you convert it into 1 millimeter here. So a 1 millimeter effective rainfall here produces this unit hydrograph. So this figure explains that actually. Okay, and what else? The volume of water in the surface runoff. Okay, so this volume, it means this volume. Okay, this is the runoff volume, right? So the volume of water in the surface runoff is given by the area under the hydrograph. So you should understand by now. So where is runoff? So runoff is the area underneath this hydrograph and above the base flow. Okay, so okay, the surface runoff is given by the area under the hydrograph and is equivalent to the 1 millimeter depth of effective rainfall. So remember, this is the effective rainfall. The effective rainfall is 1 millimeter. Okay, so this shaded, the runoff should be actually what it should be. It should also be 1 millimeter, because effective rainfall is same as runoff. That's the concept. Effective rainfall, I put SER, is same with the runoff. So it is 1 unit. If you use millimeters, so it is a 1 unit, a 1 unit of millimeter. Okay, because the effective rainfall is 1 millimeter. The runoff should be 1 millimeter as well. So that is the concept. So okay, what else? Okay, that's about it. So that is unit hydrograph. As I mentioned, after unit hydrograph of a catchment has been derived, therefore it can be used as a tool to obtain the original hydrograph of a rainfall event. Original, this means that it is not in terms of a unit hydrograph, but it is the hydrograph. Okay, so based on any rainfall or storm event at the same catchment, okay, remember the same catchment, and if this unit hydrograph is a 3-hour unit hydrograph, let's say it's a 3-hour unit hydrograph, so the unit hydrograph may be used to derive any 3-hour excess rainfall storm event. Okay, so each type of unit hydrograph according to its duration can be used to similar duration only. If it's not similar duration, if let's say you have a 5-hour excess rainfall event, so you need to convert the unit hydrograph to a 5-hour unit hydrograph, and that will be shown later. Okay, so what else? In many cases, engineer wanted to determine the peak flow. However, some projects need information about total volume and flow duration. Okay, thus the record can be obtained by using this unit hydrograph. Okay, so some if in design you will actually need just the peak flow. Some design needs peak flow, and this may be used using, for example, rational method, another method. But if you want the whole hydrograph like this one, and you want what is the volume of the runoff, okay, you want to simulate or develop this hydrograph, because you don't have any observation flow data, so you have to develop your own hydrograph. So you may use this unit hydrograph. Okay, so here are assumptions of the unit hydrograph theory. It means that some assumption for the application of this unit hydrograph. Okay, so for this first assumption, I hope you understand this one. Okay, if storm A, let's say there is a storm A, okay, this is the excess rainfall of a storm A, and the total excess rainfall is 80 millimeter. Okay, this is storm A. Okay, and storm A produces a given hydrograph. So it produces some hydrograph, some unit hydrograph. And storm B, let's say there's another storm. Storm is an event rainfall. Let's say this is storm B. Okay, and the intensity is higher than storm A. Maybe it's 160 millimeter. Okay, so here it says storm B is equal to storm A multiplied by a factor. So storm B, this is storm B, multiplied by 2 from storm A. So it produces storm B. Okay, then the hydrograph produced by storm B. So we want to know what is the hydrograph from storm B. So we may put here, then the hydrograph produced by storm B will be equal to the hydrograph produced by storm A. So this is hydrograph storm A, this is hydrograph storm B, multiplied by the same factor. Okay, so this hydrograph of storm B just multiply by 2 from storm A. So of hydrograph A. So from hydrograph A, storm A, multiplied by 2, so you get the hydrograph for B. Okay, so this is the assumption on the application of using the unit hydrograph. Okay, so there are more assumptions on the application of this unit hydrograph theory. And before I go on, I forgot to mention, like the previous assumption in the previous slide, so that what's important is the storm should have the same duration. Then you can apply these assumptions. Okay, remember, like before, storm A and storm B, so both storms should have the same excess rainfall duration. For example, if storm A is 3-hour rainfall or excess rainfall. So storm B should have also 3-hour excess rainfall. Then you can use this unit hydrograph theory. Okay, and what else? Here the time distribution. This one, the time distribution of the direct runoff is independent of concurrent runoff from antecedent storm events. So antecedent means another following storm events. So it is independent. Okay, so what you get is, for example, a 3-hour unit hydrograph. Okay, so you will produce this kind of hydrograph. 3-hour excess rainfall storm. So you will produce some type of unit hydrograph. So the time distribution, okay, of the direct runoff this time of the direct runoff or this hydrograph is independent. It's not related to next storm. Okay, so this implies that the direct runoff responses can be superposed. This superposed means that, okay, this is the example. If storm C is the result of adding storm A and B, okay, let's say you have storm A and you have storm B. Okay, so this is A, this is B, and there's storm C. So storm C is the combination of storm A and storm B. Okay, let's say where to put. So here. So this means that, let's say this is storm B, the purple color. So this is the same as storm B, and this one, storm A, so it's the same as this one. Okay, so okay, here it says okay, so this is actually what it means. If this is storm C, okay, so storm C, this storm C is the resulting of adding storm A and storm B. Storm C is the result of adding storm A and storm B. Okay, it may be this way, okay, or it may be overlay. Maybe overlay means that this B maybe is more earlier. Okay, so it overlays with storm A. Then the sum of the hydrograph, okay, produced by storm A and storm B, okay, will be equal to this storm C. So it means that you know that storm C is the it is similar to by adding storm A and storm B. Let's say storm A has this kind of hydrograph and storm B this kind of hydrograph. So storm C, the hydrograph would be the combination of hydrograph produced by storm A and storm B. Okay, so it might be like this, maybe. There's some method on how to combine it. So, but the point is here that it can be superposed. This is the keyword. It can be superposed using other storms. But most importantly, you need to know this duration. If this is a 3-hour unit hydrograph, and storm B is also a 3-hour unit hydrograph. So it is a 3-hour plus 3-hour unit hydrograph. Then you may use it. If it's not the same duration, then there's another method which we call S-curve. We need to convert that unit hydrograph. But for this case, the important thing is that it can be superposed. Superposed here. It can be superposed. So maybe you will understand more from example later. Okay, so even though from that assumption, superposed, what you need to understand also is that hydrologic systems are usually non-linear. Okay, due to factors such as storm origin and patterns, and there's a lot of type of storm. Its temporal pattern and may be different, and stream channel hydraulic properties might also be different. But if it's in the same catchment, the same stream, then this is same. But it's not that simple, and the relationship might be non-linear. So in other words, if the peak flow produced by a storm of a certain intensity is known, okay, we know that storm A produced this kind of peak flow. The peak corresponding to another storm, if there's another storm, even though with the same duration, with twice the intensity, is not necessarily equal to twice the original peak. So it is more complicated, but you may use those assumptions for more simplification. Okay, so this is an example. Okay, so for example, there is a records of observed river discharge given in the table. So you may look at your notes. So there is a table, there is an observation of river discharge shown in the table from a 2-hour storm. Okay, so this 2-hour storm, they did not show the storm, but we know that it is a 2-hour storm, occurs in watershed A. Okay, so this watershed or river basin has an area of 50 kilometers square. Okay, derive a 2-hour unit hydrograph. So please see and be aware, because it is from a 2-hour storm. Okay, and this is supposed to be a 2-hour excess rainfall. So the excess rainfall is produced from in 2 hours. So it is a 2-hour storm, occurs in watershed A. So when the storm is 2 hour, so what you will derive is a 2-hour unit hydrograph. So that this is what it means, 2-hour unit hydrograph. So you will produce a 2-hour unit hydrograph because of it is from a 2-hour storm. Okay, so this example, it shows the hydrograph observed from this 2-hour storm. Okay, so what it wants you to do, develop a 2-hour unit hydrograph, or derive a 2-hour unit hydrograph based on the given discharge record. So this discharge record, okay, it's an observed record. So observe discharge. So the first time you want to develop a unit hydrograph, you should have an observed data of the hydrograph from a specific storm. So this example shows you a 2-hour storm. Okay, so and the other thing is, you also need to know what is the base flow. What is the base flow? Okay, because you need to separate base flow and the runoff. Okay, so runoff is above the base flow, and base flow is of course the base flow. So this is most important part, to separate the base flow, and then you want to get only the runoff. Okay, so that you can develop the 2-hour unit hydrograph. Why 2 hour? Because it's from a 2-hour storm. So make sure you understand that. Okay, and what else? Assume the base flow, the time interval is 1 hour. So they want so the time interval of this hydrograph observation is 1 hour. So let's see next slide. Okay, so this is the observation data. Okay, the hydrograph, the observed discharge. So you can see here that you cannot see actually from what duration storm. It is just mentioned. So it's from a 2-hour storm. But this hydrograph doesn't mean that it will have until 2 hours. It doesn't mean it's from 0 to 2 hours. It just means that this discharge is developed from a 2-hour storm, 2-hour rainfall. Okay, and the other information given is it has an interval of 1 hour. Okay, that's another information. It has an interval of 1 hour. See, for each 1 hour it has the discharge data. Another 1 hour, another data, and so on. So this discharge hydrograph is developed from a 2-hour storm. Okay, so that is why we want to derive a 2-hour unit hydrograph. So remember, we want to derive a 2-hour unit hydrograph, okay, because it's from a 2-hour storm. Okay, and you can also see here there is some base flow. Okay, so you may estimate this base flow. Okay, starting at the second hour, there will be some runoff coming in. Starting off 2 hours, then there will be a runoff coming in. Before that, this 5, Qmax is cubic meter per second. This value of 5 is the base flow. Okay, so remember the first step is you should separate the base flow and the runoff. So how do you do it? Okay, so in the table, okay, this is the discharge, the observed discharge, and you may create another column, or if you want to minus it without this column is also alright. It's just that you have to minus tolak the discharge to the base flow. Okay, so again the first step is to separate base flow. So this table shows you again the time, okay, the observed discharge, the base flow, and what you estimate is this, the surface runoff. So this surface runoff is the production from discharge minus the base flow. Okay, 5 minus 5 equals 0. 18.46 minus 5 equals 13.46. 36.4 minus 5 equals 31.4. And so on until the end. And see here is the interval is 1 hour, 1 hour, 1 hour. Okay. So next, okay, you know this surface runoff. It's in the unit of Qmax, cubic meter per second. Okay, now you want to develop the unit hydrograph. Okay, so what you do is actually quite simple. Okay, you just need to identify what is the runoff. Okay, so what you do here, you need to divide. You need to divide by some value. Okay, so what is this value? Okay, so you know that how you get this one, the surface runoff. So be aware this is in the unit cubic meter per second. Okay, so if you want to develop the unit hydrograph, you need to divide it by, okay, you need to divide it by what? By the runoff. But okay, I know that this is the surface runoff, so you need to divide by the total runoff for this catchment. Okay, because you want it to be in the unit of Qmax or meter cube per second over in this case they want the unit hydrograph to be in 1 cm, so over 1 cm. Okay, this case, this unit hydrograph, the unit is Qmax over 1 cm. So what should we divide this from what? So we should divide it from the runoff, the total runoff, the total runoff in the unit centimeter, in unit centimeter, because we want the unit hydrograph to be Qmax over 1 centimeter. So we need to divide all the surface runoff by the total runoff. So how do we calculate that total runoff? Okay, so here, okay, we know that the area under the hydrograph curve. Okay, let's say you plot this hydrograph. The table is given. Let's say you plot them and you plot this charge. So this charge is in the unit of meter cube per second. So what you want to do? You want to develop a unit hydrograph. So this unit hydrograph, the unit of this unit hydrograph is meter cube per second over 1 centimeter. Okay, so what should we divide it? Because we want this total hydrograph. Okay, this runoff, just the runoff. We just want the hydrograph of the runoff, which has the runoff as 1 centimeter. So this should be 1 centimeter. Okay, but now it's not. Now from the observed data, okay, so what is the runoff in terms of depth? What is the runoff? What in centimeter? What it is? What is it? So this is how you calculate it. So the area under the hydrograph curve is the volume of surface runoff. It's actually the volume, the area under the curve, because meter cube per second you multiply by the time, multiply by the time. This meter cube per second multiply by second, you will get meter cube. But we don't want meter cube. We want it in the unit centimeter. We want in the unit centimeter. So what you do is here. Okay, the total area of trapezoid with 1 hour wide means that if you make it in a trapezoid form, like this, like this. So it means here that for one trapezoid, this is one trapezoid, one section. Okay, the total area of trapezoid with 1 hour wide. Okay, because we know the data is this is the data is 1 hour. The interval of the data. Okay, let's say this is the data is here and here and here and here. So it's the interval is 1 hour. Okay, so we know that. So we can measure or calculate this trapezoid volume. So it is, for the first one is 3 4 sorry, not for the first one. Okay, the total, okay, because this 347.23 is the total of all this trapezoid. So the total of all the trapezoid, you multiply by 1 hour. Because the unit here is meter cube per second and the data is in the interval of 1 hour. So you can estimate this whole area under this graph. Okay, you can estimate it by using this calculation. You can use this calculation, which is the total runoff. So this is a meter cube per second. Meter cube per second. You multiply by 1 hour. Okay, 1 hour. So 1 hour, but you want it to be in the unit. Let's say here in the unit meter cube first. So you need to convert that 1 hour to second, and that's why it multiplies 60 multiplied by 60. This is a conversion factor from 1 hour to second. That is why 60 multiplied by 60. So here you already multiplied by the 1 hour, or 3600 seconds. So you will get these values: 1.25 exponent 6 cubic meter. It's already in meter cube. So this is the volume of surface runoff. 1.25 with the power of 10�6 meter cube. Okay, but remember, you want it to be in this unit centimeter. Okay, so what do you do next? Okay, so you know that it is in meter cube. You calculated before in unit meter cube. You already exposed the second because you multiply by 1 hour. Okay, the time interval is 1 hour, so you multiply by 1 hour, so you will only get the volume of the surface runoff. So now, instead of volume, you want it in the unit depth, in meter. So what you do is you divide by the catchment area. Okay, why is this? Why you divide by the catchment area? Because let's say this is your catchment, okay, and this catchment produces a runoff. It produced this runoff. Okay, in volume, in meter cube, okay. But okay, this area of catchment produce this meter cube of volume of surface runoff, but you want it in the unit meter. Okay, so what you do is just you divide it by the area of catchment. So what you have is actually for a catchment. Oh, where is the for a catchment? So when you divide by this volume, it seems like in 1 unit area, in 1 unit area. So this value that you get here is in depth only, in this one point. It's not for the whole volume. It's in 1 point. So that way you get this 0.0.25 because you divide the volume divide by the catchment area. So what you get is this. Is in the unit of in meter. Okay, so remember that for the unit hydrograph, you want to find unit hydrograph, and don't forget that. So so this unit hydrograph, the unit is meter cube per second for a 1 millimeter effective rainfall. So what you do, okay, effective rainfall is same as runoff, right? So this is the effective rainfall, 25 millimeter. So this is the 25 millimeter. So this is the effective rainfall. So what you do is for each surface runoff, okay, you divide by 2.5. That is how you get this value 5.38. And for the first row 13.46, you divide by 2.5. Or here for simplicity it converts 1 over 2.5 into 0.4. So that is why it multiplied by 0.4. So you get the 5.38. Okay, and for the next row also multiply by 0.4. So you get this, and so on. So this is the ordinate or the value for the unit hydrograph. Okay, so these are the value for the unit hydrograph. Okay, so just to show you again the whole process again. So okay, this is given to you. Okay, this is given to you. So you know the discharge. Okay, so you find out what is the base flow. Okay, so in this case the base flow is 5 cubic meter per second. So you want just the surface runoff in unit cubic meter per second. So what you do is just you minus discharge minus base flow. So you get the surface runoff in the unit cubic meter per second. Okay. So next, after you get this surface runoff, now you can find what is the value for the unit hydrograph. So what you do is you remember you divide by the total runoff, okay, in the unit depth. For example, because you want this unit hydrograph in the unit depth of per 1 centimeter, so you divide it by 2.5 centimeter. So how you get this 2.5 centimeter? It is as I explained before. Okay, so this is actually the total runoff for that particular catchment in 1 unit depth of centimeter. Okay, so the total runoff is 2.5 centimeter. So you want it in a 1 unit depth, so you divide all this surface runoff in unit Qmax, divide by 2.5. So you get this unit hydrograph. That is why the unit for this unit hydrograph is actually Qmax over 1 centimeter. Okay, because you divide by 2.5 centimeter. Okay, so divide by 2.5, divide by 2.5 until the end. So now you will get this unit hydrograph. Okay, so let's see how we can plot this. So just as hydrograph or discharge, we can plot this unit hydrograph. Okay, so if you look at this, it's actually same as the hydrograph, just the difference is here. Okay, the ordinate changes, because this is actually in the unit of Qmax over centimeter, 1 centimeter. Qmax over 1 centimeter. So this is the units of the unit hydrograph. So if you calculate back the runoff, the runoff in unit centimeter, all this under the area under this curve, what should you get? You should get 1 centimeter. Okay, so you can try. Try to get this area under the graph in the unit 1 centimeter. Means that you need to divide by the catchment area, and then you get this in this unit of centimeter. So you should get 1. Okay, and here you can see that this is the new QP. The TP should be same. TP should be the same, just the QP, the intensity of this Qmax meter cube per second changes. Before it was, I think it's 66. But now because of unit hydrograph, we had divided it by the total runoff, so this QP becomes 24. So check in your table. Before the original hydrograph, this is I think 66, but now it becomes 24. This is because we had converted it in the form of unit hydrograph. And remember, this 2 hour has what is it? It's actually this unit hydrograph is derived from a 2 hour rainfall. 2 hour rainfall, excess rainfall event. So that means that 2 hour. Okay, let's say you want to check whether your unit hydrograph is correct or not. So again, from the unit hydrograph ordinate, you can sum up all the runoff, and then you get 138.88. And then what you do is calculate the runoff in unit cm, in this unit. So how do you do that? So you remember the catchment area is 50 multiplied by 10 power of 6 meters square. So therefore, what you do is, first you want to eliminate this hour, the time. So what you do is the total runoff, in unit meter cube per second, you multiply by the time, in second. So then you get the volume, just the volume. So this is the volume, not the meter cube. But now you want it in the unit of depth, in the unit of meter. Specifically, you want in the unit of centimeter. So what you do is this value, the volume, you divide by the catchment area. Same process as before. You divide by the catchment area. So you want to see whether your runoff in the unit centimeter is 1. This is 1. So what you get is 1. Because we have calculated it right, and we had divided by 2.5 cm. 2.5 cm is the runoff for that catchment in unit depth. So if you try to calculate again the runoff in unit depth, specifically in the unit of centimeter, you should get 1. For this example. So for other cases also, if you derived it from to meet unit hydrograph in the unit of over 1 millimeter, then you should get 1 millimeter. Or if you derive the unit hydrograph in the form of unit meter cube per second over 1 inch, then if you check again, you should get 1 inch. So because this example is in the unit of over 1 centimeter, so if you recall back and calculate back the runoff in unit depth, so you will get 1 centimeter. So this means that the total runoff is in unit centimeter is 1 cm. So this is correct. So our unit hydrograph is correct. So for this chapter, the first assignment will be this, and the information on this assignment and deadline are given in e-learning. Once you develop the unit hydrograph, so now you may use it. You may apply it and use it to develop a specific hydrograph based on some storm. So the storm must have a similar duration with the unit hydrograph. So for example, you already derived a 2-hour unit hydrograph. So the storm should be a 2-hour storm. Okay, so for this case, we want to develop a hydrograph for multiple storm events using using unit hydrograph. So the temporal storm pattern is illustrated in the hydrograph given in the next slide. Okay, so see here we have 1, 2, 3, 4. Okay, 4 storm, and each of this storm has a 2-hour. It's a 2-hour. It's actually like 6 plus another 2-hour storm, but you can separate it and make it individually, like storm A, storm B, and storm C, and storm D. So using the 2-hour unit hydrograph, you may superpose how do you say impose this multiple storm using the unit hydrograph, such as have mentioned before, the assumption that you can use by using unit hydrograph. So you can superimpose this storm. Okay, so storm A is 2-hour storm B is 2 hours, storm C is 2 hour, and also storm D is 2 hour. So you may use this 2-hour unit hydrograph. So let's see how you do it. Okay, so here is the detail of this storm event. There are 4 storms, storm A, B, C, and D. So from the hyetograph, we know that it is a rainfall intensity, excess rainfall intensity in the unit, this millimeter per hour. Okay, but in order to use this unit hydrograph, so we need to convert the rainfall, the excess rainfall, in the unit depth in millimeter. Okay, we don't want millimeter per hour, we want millimeter. So we have to calculate what is the excess rainfall depth for each storm. So for storm A, it's a 15 millimeter per hour rainfall intensity. So you multiply by 2 hours. Okay, because the time duration is 2 hours. See back the hyetograph. So you get 30 millimeter. So 30 millimeter is the excess rainfall depth for storm A. Okay, and then for storm B, also you multiply the rainfall intensity to 2 hours, and you get this 60 millimeter rainfall depth, and so on. C, you get 20 millimeter. D, you get 25 millimeter. So this value, okay, this excess rainfall depth, this is the one which you need to use to get the hydrograph. So let's see the next step. Okay, so just recall back the unit for the unit hydrograph is meter cube per second over per 1 cm. Remember, it's per 1 cm. Okay, so what you do, you have this excess rainfall. Okay, you get from the rainfall hydrograph. So after that, you need to multiply this excess rainfall to the unit hydrograph ordinates. It means that okay, you know that this is the unit hydrograph, right? So UH means this this Q. You need to multiply by each of these Q. Okay, so why this is divided by 10? Because the unit hydrograph is in the unit meter cube per second per 1 cm. So you want this to be in unit cm also. Okay, you are converting this to unit cm. That's why you divide it by 10. So you have to follow what the unit hydrograph unit is. So this unit hydrograph is meter cube per second over 1 cm. So you have to multiply by cm in centimeter also. Okay, you have to multiply the excess rainfall depth in centimeter. That's why here you divide 10. Okay, so simplifying it, it becomes 3 multiplied by the unit hydrograph. Unit hydrograph means the Q, multiplied by the Q. Okay, and so on for all of the storm. This is storm A just now, storm B, storm C, and storm D. Okay. Okay, so just just to make it more clear, so this is for each rainfall event A, B, C, D. So we have the excess rainfall, and we calculate this surface runoff from the UH. We calculate the surface runoff. But remember, this surface runoff, the unit is still meter cube per second. Meter cube per second. Okay, but it will not be a unit hydrograph anymore. Once you multiply by the storm excess rainfall, it will not be the unit hydrograph anymore. It will be the hydrograph. It will be just Q with the unit meter cube per second. You have already eliminated the per 1 centimeter depth. Remember, unit hydrograph, the unit of the unit hydrograph is meter cube per second over, I put here per, over 1 cm, right? So, but you have already multiplied the excess rainfall. Remember here? So now this has been eliminated. It means that it's not a unit hydrograph anymore. Okay, it's a hydrograph. This is the hydrograph. For the runoff, the hydrograph for the surface runoff only. So this will be in the unit meter cube per second. You have eliminated this over 1 centimeter. Okay, to see it more clearly, so let's say this is the 2-hour unit hydrograph you have developed. Okay, so you have developed this 2-hour unit hydrograph, and see the peak discharge is 10.23. Okay, this is the 2-hour unit hydrograph. Okay, this is the unit hydrograph. So what you did just now is you are multiplying all of the unit hydrograph, see, to the storm runoff. Okay, to the storm excess rainfall. You are multiplying the unit hydrograph to the storm excess rainfall here. This 3, 6. So these are the excess rainfall. Okay, so you multiply it. Remember, before the unit hydrograph is different. So this is the product of the, you multiply it with the excess rainfall. So for storm A, for storm B, for storm C, and storm D. Okay, and another thing that you need to realize is, see here. Okay, storm A starts at 2 hours, so it will start here at 2 hours. Okay, storm B starts at the 4th hour, so it starts here at the 4th hour. Okay, storm C start at the 6th hour. Okay, so here start at 6 hour, and storm D starts at 12 hour. So this is starting from 12 hour. Okay, so there are several things here. First, you need to multiply each unit hydrogram to each storm excess rainfall. So here is it. Here it is. Okay. Next, where do you put the production of the hydrograph production? So you put it or you you arranged it according to the time here. Okay, because storm A starts at 2 hours, so you start at 2 hours. Storm B starts at 4th hour, so you start at 4th hour. Okay, so I'm just repeating. Okay, so and then what you do is you need to add the base flow. Okay, remember this before, this is just the runoff. What you are doing here at this left part is just the runoff. So now you need to add with the base flow. Okay, because you want the hydrograph. You don't want unit hydrograph anymore. You want the hydrograph. So this is the hydrograph in the end. And what you do is you add up. Okay, let's clear things up. Okay, so you add everything here. So you add 0, this row at 2 hours 0 plus base flow 5. Okay, at the 4th hour, storm A has some runoff contribution, and then storm B at 0, storm C not yet, storm D not yet, base flow yes, so you add. At 6 hour, storm A contributes to some runoff, storm B contributes to some storm runoff, storm C not yet, base flow yes, so You add up, and so on. At 8 hour, storm A has some contribution, storm B has some contribution, storm C has some contribution, base flow, and the total hydrograph. So see, so this is the not arrangement, the calculation on how you get the total hydrograph. So you do it all until the last hour that has some data. Okay, so in the end you get the total hydrograph. So in the end you get the total hydrograph. Okay, so you have learned how to apply the unit hydrograph to develop a new hydrograph based on any storm that you get. So this is your assignment 2. Just do the same thing using Excel. Use the cell formula. Okay, I want to see the cell formula. I will check. And then plot the derived hydrograph. I want to see the end product, the last, the total hydrograph. Okay, and then please compare the peak discharge that you get compared to the unit hydrograph peak discharge. So this would be your assignment 2. Okay, now another important thing on the application of unit hydrograph is you can convert the unit hydrograph duration. Okay, remember I told you that before we use 2-hour unit hydrograph, right? Oops, 2-hour unit hydrograph. Before we used 2-hour unit hydrograph, right? So now this 2-hour unit hydrograph can only be used for storm with 2-hour, okay, with 2-hour excess rainfall. So what if the storm is not a 2-hour excess rainfall storm? So you cannot use a 2-hour unit hydrograph because this is a 2-hour unit hydrograph which is generated from a 2-hour storm. So if you have another storm with an excess rainfall storm with a duration of 3 hours, you cannot use this 2-hour. Okay, so you have to convert it into a 3-hour unit hydrograph. So this is the method on how do you want to convert the unit hydrograph T. You want to convert this from 2 hours to 3 hours, from 3 hours to 2 hours, from 1 hour to 5 hours. It doesn't matter. Okay, so you can convert it. So the method is using the S-curve method. So this is how you do this method. Okay, so let's see the next slide. Okay, so what is this S-curve actually? So before, the slide before is 1 unit. 1 unit. Let's say this red rainfall is a 2-hour excess rainfall. Okay. So what you do is you make it into a continuous rainfall hyetograph. It's a continuous rainfall hyetograph. So what you get is this kind of repetitive of hydrograph, of the unit hydrograph. So S-curve is the cumulative of this repetitive hydrograph. This one. More specifically runoff, because it's just the runoff. Unit hydrograph is just the hydrograph of the runoff. So this runoff generated from continuous rainfall hyetograph. But the S-curve is the cumulative of this. This is the curve. So you can use this curve to convert it to any period, any duration, any unit hydrograph duration. So let's see the next slide. Okay, so now there is no other way, or the best way is just by using an example. Okay, so for the first step, for example, you want to convert a 4-hour unit hydrograph. You want to convert it to a 3-hour unit hydrograph. So the first step is you need to develop the S-curve for the 4-hour unit hydrograph. Then you can develop the 3-hour unit hydrograph using the S-curve of the 4-hour unit hydrograph. Okay, so let's see how. Okay, so this is actually the step. Okay, So you have a 4-hour unit hydrograph, okay, in the in Qmax. Okay, so this is Qmax over 1 cm. Probably I didn't write here, but most probably it will be in unit Qmax over a 1 cm depth. Okay, so this is the 4-hour unit hydrograph. So this first column is the 4-hour unit hydrograph. So you want to develop this S curve. Okay, so this is the S curve. Okay, so how do you do that is because it's a 4-hour unit hydrograph, so you need to delay 1 2 3 4 1 2 3 4 4 hour, delay 4 hour. Okay, you start at 4 hour. Okay, so the first cumulative is you start at 4 hour, so it's just a repetitive. So this is also the 4-hour unit hydrograph, but you delay it at until 4 hour. Okay, so this is delay it again to the next 4 hour, delay it again to the next 4 hour, okay, and so on. So what you do is you get this. How do you get this S curve? You just add up, add each row each time. This is 8.8, still 56.8, still 99.2. Then at the 4th hour it will start to have it should start to add up. So this is 0, so it's still 136. So the next, the 5 hour, 158.4 plus 8.8. So it already add up. Okay, so add each row. I hope you understand this. So this is the product of the addition. So these are all the cumulative from each time. For each time. Okay. So this is the S curve. So this is the S curve. Okay. For a 4-hour unit hydrograph. Because it's a 4 hours, so you delay it 4 hour, and you cumulative it to get the S curve. So if you plot it, you will get this kind of shape. And how do you know how many times you want to add? Add the unit hydrograph. So it depends. Until you get a constant here. Okay, until you get a constant here. Okay, so before you created a continuous rainfall hyetograph using the 4-hour unit hydrograph, so you get this S curve, right? Okay, so the next step is you displace 3 hour because you want to convert it into 3 hour. So you displace this S curve with the period of 3 hour. Okay, displace 3 hour. The S curve, displace the S curve for 3 hour. So let's see. You may see it more clearly in the table form. Okay, so this is the S curve for hour. This is S curve already, and not unit hydrograph anymore. It's the S curve for 4 hour. So you want to convert to a 3 hour unit hydrograph. So you have to displace this S curve. 3 hours. 1 2 3. Okay. So start here. Start here. Okay. 1 2 3. Start here. Okay, so this is a 3-hour displacement. Okay, what else? Okay, so next you have to find the difference between this 4-hour S curve and the 3-hour displacement. So this is the displacement. This is the S. Okay, so you minus it. 0, so 0. 8.8 minus nothing, so 8.8. 56.8 minus nothing, so 56.8. 99.2, still you get 99.2. At this time you get 136 minus 8.8, you will get 127.2. 127.2 minus 56.8, you get 110.4, and so on until the end. You minus it. Okay, until you get 0 here. Okay, that is why you have to have some constant here. So until you get 0. Okay, so in the end, not finished yet. So how do you get the 3-hour unit hydrograph? You need to convert it this way. So this difference, this column, I put number 1 2 3. Okay, the product of the difference, column 3 here, column 3, Okay, you multiply by 4 divide by 3. Okay, multiply by the original S curve, divide by the S curve that you want to get. I put SX. So the original S curve, which is unit hydrograph 4 hour, divide by the intended unit hydrograph. So I put X here, so it is 3. Okay, so column 3 here, the difference, you multiply by 4 over 3, and then you get this. Okay, so this is the in the end, this is the product. This is the 3-hour unit hydrograph. Okay, so this is the step to convert the duration. Oh, okay, so this is basically the content of chapter 5 here, okay, until S curve. And so S curve is to convert the duration. So for unit hydrograph, you must understand what is unit hydrograph and what it represents, what it is used for, how do you develop it, how do you apply it, and application also involve how do you convert the duration. So this is for chapter 5. So hydrograph, unit hydrograph. So unit hydrograph, it is applied a lot actually, even in modeling, in computer simulation or modeling. For hydrological modeling, we use this. It's in the even if you use your software, you have to understand how it works. Okay, so thank you for watching.